Yeah, it was using my tablet's mic. Better. Right. So the point is that if you draw a line from your gravitating body to your orbiting body, like this line here, and then you ask the area of the wedge that's swept out in a certain amount of time, it doesn't matter where in the orbit you are, the area of that wedge will always be the same, even though you might cover more angle when you're closer to the body. You cover that angle faster. And so this is a statement of Kepler's second law. And really what it teaches us is, or what it tells us, teaches is such a weird word. What it tells us is that the average speed, or the speed of the orbiting body when it's near perihelion, or near periapsis, which is the term for just generic orbits, is higher than the speed when it's near aphelion, or apoapsis, which is, again, the generic term. And that's just because if the speeds were the same, then they would cover the same angular, well, they wouldn't necessarily cover the same angular distance, but they would cover, but you could see pretty clearly that their areas wouldn't end up being the same. So we're going to move on to Kepler's third law. So Kepler's third law is, unlike Kepler's second law, perhaps, is slightly more mathematical. And it's just a statement about the orbital period versus the semi-major axis. So the statement is that the square of the orbital period of an orbiting body, so the orbital period is just the time to do one orbit, is directly proportional to the cube of its semi-major axis. So this is just a statement of proportionality, and with regards to proportionalities, you can always rewrite them as some quantity, which is typically the ratio of the two things that are proportional, equals a constant. So we can write this mathematically as the following. It's just that t squared is proportional to a cubed, a being the semi-major axis, remember. And so what we can do is we can rearrange this equation. We get that t squared, the typical way it's done is a cubed divided by t squared is proportional to 1, i.e. a cubed divided by t squared is a constant. And so this is typically how Kepler's third law is presented. It's presented as the fact that for any given gravitating body, if you have two separate orbits, one orbit with semi-major axis A1 and another orbit with semi-major axis A2, then if you cube those semi-major axes and divide them by the square of their respective orbital periods, you'll get the same number out, which is kind of amazing because that means that we can determine the shape of another object's orbit just from knowing stuff about our own orbit. For example, we know the Earth's orbital period is about 365 days. We also know we can measure how far away the sun is from the Earth, and that will give us approximately the semi-major axis. And so, for example, if we can figure out what the orbital period is of, say, Mars, we don't even need to know anything else, and we can figure out what the semi-major axis is of Mars's orbit. There's a lot of the power of that particular statement is really high because you can learn a lot, and we're actually going to use Kepler's third law in the homework. And this is something that you could have shown using Newton's laws, but the point is that Kepler determined this without knowing Newton's laws, which is kind of amazing. It was 20 years before. I think it may have actually been even before Newton was born, but I'd have to double check that. So let's just work out a quick example of where this might be relevant. So one might ask, how high must a satellite orbit above the Earth? And we're going to assume everything is a circular orbit because it just makes our calculations easier. Orbit above the Earth, but to ensure that it is always above the same position on Earth, to ensure that it is geostationary, is the technical term. So what I mean is that what it means for a satellite to be geostationary, to always be above the same point on the Earth, is that it means that it takes exactly 24 hours, or exactly 1 full day, for the satellite to orbit the Earth. Because if the Earth turns in 24 hours, then the rate that the two bodies will track each other, like let's say that you have, there's the Earth and there's your orbit, after 6 hours, the satellite would have moved here, and it's still above the same position. And after another 6 hours, it would be here, and the Earth would have turned another 90 degrees, and so on and so forth. So this keeps the satellite always above the same point. And this is useful for like telecom satellites, by the way. Geostationary orbit is a very expensive place to put satellites because so many people want to put satellites there. So it's important. So we know that t has to be equal to 1 day. And also we know that it has to be above the equator, because if it's not, then the whole thing would, like, you can orbit at a different angle, but it would make things not line up anymore. So what we have from Kepler's third law is that there's some constant which is equal to the radius of the orbit. This will tell us something about the altitude, cubed, because we're assuming it's circular, divided by 1 day squared. And so what we're going to want to do is determine this constant and then use that to solve for the radius of the orbit. So in order to determine this constant, you can either A, calculate it explicitly, we'll come up with a formula for it later, or you can just use another orbit that we know more about to determine the constant. Now, in particular, we know things about a very particularly large satellite that orbits the Earth, namely the moon, right? We know the period of the moon. We know exactly how far away the moon is because we've been there. So we can determine the constant just from the data that we have regarding the moon. It turns out that the moon, the orbital period of the moon is about 27.32 days, approximately. And the semi-major axis of the moon, assuming that the moon's orbit is roughly circular, which it is, it can be measured directly. You shoot a laser at the moon, you wait for it to bounce back, and then you time how long it takes to get there. This is, again, roughly 384.4 megameters. By the way, a lot of places they'll use like 384.4 thousand kilometers. I prefer to use SI units and prefixes. So you'll see me use megameters, gigameters, because it's more fun that way. And technically, it's more correct. So this just means 384.4 million meters. So that means that 384.4 megameters cubed divided by 27.32 days squared is equal to that constant, because the gravitating body is the same. It's still the Earth. And so this should be equal to r cubed of the orbit that we're interested in, this geostationary orbit, divided by 1 day squared. Now, you could work out the math. It works out that the left-hand side looks like 76,458 cubic megameters per square day, which is a really weird unit, but, you know, sue me, it's a totally valid unit. And so this should be equal to, you know, the orbit squared, sorry, the orbit cubed divided by 1 day squared, 1 square day. What does a square day look like anyway? Is it like a square meal? I don't know. And so we can solve explicitly for this, our orbit. You just take the cube root of both sides. You can multiply both sides by a squared day first. But the solving, we get that the orbit is equal to the cube root of 76458 megameters, which is approximately 42.4 megameters. And that it turns out that, well, we should take into account the fact that this is measured from the center of the Earth, right? Because we're the gravitational force is always applied at the center of mass, and the center of mass of both these systems is approximately at the center of the Earth. So this is, you know, 42,400 kilometers from the center of the Earth. So what is the so then you can ask, okay, well, what is the actual value? Like, how accurate is this calculation? It turns out that the actual height of geostationary orbit is 42,164 kilometers, which, all things considering, pretty good, right? You know, it's less than 1% error, so I would count that as an absolute win. Anyway, so you can use this kind of trick a lot to find to get to high degrees of accuracy what these values are. Now, by the way, the reason why there's an inaccuracy and it's not exactly right here is because the center of mass of the Moon Earth system is actually not quite at the center of mass of the Earth, because the Moon is fairly large. It's fairly large as far as moons go. The center of mass of the satellite Earth system is almost precisely at the center of the Earth, because the satellite has a negligible mass, but the Moon is large, so it does affect the calculations. Now, all of these laws, Kepler's first, second, and third laws, I don't know why they always come in threes, but they do. All of these laws can be derived explicitly from Newton's laws of, or Newton's universal law of gravitation, which, by the way, I will be abbreviating U log. So A is just the length of the semi-major axis of the orbit, whether the path is circular or elliptical. Yes. Is that the radius of the Earth plus the height? Yes, yes. So both of these heights are measured from the center of the Earth, so you'd have to subtract off the radius to get the actual height above the surface. So all of these laws can be derived from Newton's universal law of gravitation, and so with the exception of the first law, we can actually do that, and I'm going to show you the derivation. So let's talk about Kepler's first law with regards to Newton's universal law. Because that's just not true. The third law applies for all orbits, but I used it to calculate the radial orbit of, the orbital altitude above for a particular orbit I was interested in. But it's not only true for geostationary orbits. This is just a true statement regarding orbits about a single body. And it has to be the semi-major axis, because that is what the math tells us it has to be. And we'll derive that. So we're going to talk about Kepler's first law. Now, unfortunately, so Kepler's first law, remember, is a statement about that that's too far. That the paths of bodies that are in orbits form closed ellipses. Now, unfortunately, it's kind of beyond the scope of this course to show you that that they are ellipses, but we do have enough math to show that they're closed. So so what we're going to do is we're going to prove that trapped bodies have to be closed, meaning that they don't do this forever, and they always come back after traveling through 2 pi. Now, it could have been that maybe the orbits are box-shaped. That we can't prove yet. I mean, one can do it, but you guys don't have the math for it, but it's doable. So we're going to answer the question, why are the orbits closed? And we're going to use Newton's second law to show that. So that is, come on, right. When going through an angle, why is the orbital distance the same? That's what it would mean to be closed, right? You're the same distance away, and you're at the same, and you've gone through 2 pi radians of angle, so that would mean that you're at the same position. So here's a proof. I'm going to put proof in quotes because it's not entirely a mathematically rigorous proof, but we're going to use Newton's second law, as we typically do. So instead of writing ma, or f equals ma, I'm going to write f equals m times the time derivative of velocity. But those two things are interchangeable, right? Acceleration is the time derivative of velocity. So we have minus gm little m. Right, so it isn't closed, but so if Newton's universal law of gravitation was true, they would be closed. They would be exactly closed for 2-body systems, but Einstein's gravity kind of gets in the way. And orbital decay has nothing to do with any of this. Orbital decay is because of friction. So if we're only concerned with Newton's law, with the universal law of gravity, then it would be precisely closed. So capital M is the big gravitating body, lowercase m is the mass of the small orbiting body. That's just the notation that we're going to use. So negative gmm, over r squared in the r hat direction. Remember, r hat goes from the gravitating body to the orbiting body. This is equal to little m times the time derivative of the velocity, right? This is f, this is ma. Now we can use the chain rule on the right-hand side. So, oh, that should be dt. So I'm going to rewrite dv dt as something else. So we have m times dv d theta times d theta dt, right? This is how the chain rule works. You basically multiply and divide by d something. I mean, at least as far as symbolically goes, that's just fine. This is equal to minus g capital M little m over r squared in the r hat direction. I'm going to cancel off these m's just to make it easier. So, okay. Now, what else do we know about gravity? Well, we know that the gravitational force points in the radial direction. And so that means it's a central force. It points from a certain source. So because gravity is a central force, remember when we talked about these, that means that the torque that gravity exerts is 0. And that implies that the angular momentum is conserved. And so what does that mean? It means that the magnitude of the angular momentum is just a constant, regardless of what your angular or radial position is. It's just a constant, and it's actually often called a constant of motion. So if you wanted to describe an orbit, one of the terms that you might want to provide, one of the points of data, would be the angular momentum, because that angular momentum is a characteristic of that orbit. It doesn't change as you go along the orbit. So we can compute the angular momentum of the Earth, or sorry, of the smaller body. This is just m times r squared times omega, right? Assuming that the body is sufficiently small. Obviously, we're making some points here, but the idea is that this distance here, this distance r, is significantly greater than the radius of the smaller body. And so that we can just treat it as a point mass and just compute the angular momentum as if it were a point mass. And by the way, this is a good approximation. It is the case that the angular momentum, for example, of the Earth about its own axis is very, very small compared to the angular momentum of the Earth about the sun. Right, so omega, by definition, is the second time derivative, or is the time derivative of the angle, right? The angle theta. So we can do some substitution. We can substitute in for d theta, L. So what do we get? We get that dv d theta times L over m r squared equals negative g capital M over r squared in the r hat direction. All I did was I substituted in d theta by dividing L by mr squared, and then I left the right-hand side the same. And you'll note that the r's cancel out now, which is kind of remarkable. So what we're left with is that dv d theta, this is how the velocity vector changes with the angle, and it makes sense that it would change with the angle because at least it's changing direction. This is equal to negative g times m times little m, that little m would pop up there, divided by L in the r hat direction. And the important part is that for a given orbit, this is a constant. That term up front, it's just a number. And it doesn't depend on where you are in the orbit, it's just a number. So what does that mean? Oh, by the way, just an aside, we can use the typical coordinates to describe, oh, where'd the chat go? There it is. We can use the typical coordinates to describe our orbiting body. If here is our origin and then our orbiting body's over here. The vector r hat can be described in terms of the angle because it's a unit vector. So this r hat vector is just cosine of theta I hat plus sine of theta j hat. So we're going to use that here. So what do we have? This is just something that depends on theta over here, or a derivative with respect to theta. Then we have a constant times stuff that depends on theta. So we can just integrate both sides with respect to theta. And what we're left with is that we get that v of theta, of course, is minus g capital M little m over L. And now I'm just so that was a constant. I can pull it out from the integral. And I'm just going to integrate this with respect to theta. So it's going to be sine of theta in the I hat direction minus cosine of theta in the j hat direction. And then we need a constant of integration. In this case, it's a vector of integration, as it were, because there's 3 components here. Now, the reason why I went through all this effort was to illustrate that if you plug in theta plus 2 pi, well, the only things that depend on theta are the sine and the cosine, but both sine and cosine are the same if you add 2 pi to the angle. So this is equal to v of theta. So the velocity vector doesn't change if you've once you've gone through 2 pi. So you're moving in the same direction with the same speed. And so what this implies is that v squared of theta is equal to v squared of theta plus 2 pi, i.e. after you've gone through 2 pi, you have the same v squared as you did before, and hence we get that the kinetic energy is the same whether you've gone through 2 pi or 2 pi degrees or 2 pi radians or not. But gravity is conservative. Right? We know this to be true. So that means that if the change in kinetic energy is 0, that tells us that the change in potential energy must be 0, right? Because there's no external forces, the gravity is the only force here. And so if it's the case, if it's true that the gravitational potential energy function, whatever that may be, I haven't told you what it is yet, I'll tell you at the end of lecture today, whatever the gravitational potential energy function might be, as long as it only depends on the distance from the body, then that means that if delta PE is 0, that would imply that delta R is 0. And so if we have this, if that's the case, and I'm telling you right now, it is the case, and it shouldn't be surprising, by the way, like this only depends on the radial distance and the radial direction, so the gravitational potential energy should only depend on the radial distance. If that's true, then that means that R of theta equals R of theta plus 2 pi. And so that means that not only is that means that after traveling through 2 pi radians, you return to the same distance, and you have the same velocity vector, so you're going in the same direction. So it has to be a closed orbit, because your initial conditions are repeated, and so you have to be repeating yourself over and over again. Now, so that's the proof. I know I went fast, but the idea is just that we can use Newton's laws to tell Newton's laws and just doing some integration. No, Brianna, they do not. That whole business goes out the window because of quantum mechanics. However, if you just use classical electromagnetism, then it's valid. But yeah. I'll move back down in a minute. I just want to summarize. The whole point is that we just used Newton's laws and integrated once, did some clever math, to show that it has to be a closed orbit. And you can do the same for the rest of Kepler's first law to show that it has to be a closed elliptic orbit, but that takes a little bit more work. By the way, just a quick note here, note about this proof. This only worked because the force is proportional to 1 over r squared. If it was, say, proportional to 1 over r cubed, then our very first step where we canceled out these r's, that would not have happened, right? The r's would not have canceled out and none of this would have worked. So it actually relies on the fact that Newton's law, universal law of gravitation, goes as 1 over r squared. That's very important. By the way, I'm going to give you a hint for homework problem 6. So in homework problem 6, I ask you to find the ratio of the velocities at the perihelion, or the ratio of velocities at perihelion and aphelion. Meaning, if you have, say, an orbit like this, I want you to find the ratio of the velocities here to here. Now, the way to approach this problem, I'm not going to give it away, but the way to approach this problem is use the fact that the angular momentum is conserved, regardless of where you are on the orbit. And then you can use the fact that the angular momentum is mv times r perpendicular, where r perpendicular is the perpendicular distance. Whatever result you get for problem 6, your result should be in terms of the eccentricity of the orbit and perhaps the semi-major axis. It's going to involve some geometry, so go back and brush up on your ellipse geometry, but it's really not a hard problem. So just a hint. By the way, it takes some work to do that, to get this result, and I'm going to skip over it, especially because some of it is homework problem 6. But it is true that after some work, we obtain the result that L squared is equal to A times 1 minus E squared times G capital M lowercase m squared. This is just is there a valid way to do it where you integrate Kepler's second law? Because that's what I did. Yeah, no, that's precisely, that's a perfectly valid way to do it. It's just slightly easier if you use angular momentum. But you can't really use this, like this equation, I'm not gonna let you use this to answer problem 6 because this requires the answer from problem 6 to get. So don't use this to get to problem 6, it's not fair. That said, we can substitute that equation. By the way, this equation is useful, so that's why I'm gonna put it in a box. We'll use it later. We can substitute this into the formula that we had for r of theta, and we get r of theta equals L squared over capital G capital M little m times 1 over 1 minus E cosine of theta. This is just a truth. This is all I did was substitute this into here. And this is just a convenient formula that you can use to write out the formula for the ellipse. Right. All right, moving on, let's derive Kepler's second law. So Kepler's second law is the statement about sweeping out equal area orbits. So we can handle this infinitesimally. That's typically what you do when you're doing calculus. You do the infinitesimal case and then you integrate to find the general case. So we're going to look at the infinitesimal case as normal. Or perhaps not as normal, but as would be expected. So here's our ellipse. Say here's our let me draw the semi-major axis and the semi-minor axis. Here's one of our foci, one of the focuses. And let's say that we want to find the area between these 2 points. So, and let's say that that's an infinitesimal length. Let's call this angle d theta, infinitesimal. This arc would be r d theta. All I'm doing is I'm just filling out. And then this length here would be dr. Right. So if the angle d theta is infinitesimally small, then dr is also infinitesimally small. That arc length would be infinitesimally small, but you multiply by r to get the arc length. So on and so forth. Nothing sneaky going on there yet. And so what we can do is we can just compute the area of this quote unquote triangle, right? We have a triangle that looks something like this. We have the angle d theta. We have this length is r d theta. We have this length, which is dr. So how do we compute the area? So the area, let's call it dA, would be 1/2 times, well, we need the, oh, and this distance here would be r, hence the radial distance. So this would be, so it's a triangle. So it's just, let's compute the area of this triangle first. Would be easy. By the way, that distance is also r, unfortunately. So it's 1/2 times r d theta, right? Base times height. Oh. Is that dA equal to 1/2? And then it's plus, that should be a dr there. There we go, triangle's done. Plus 1/2 base, the base here is dr, times the height, r d theta. Now, the important point to note here is we're interested in how long, or how much area is swept out in a given amount of time. So what would be useful is like the rate of change of the area with respect to time. So what we do is we can write dA dt. This is equal to 1/2 times r squared d theta dt. 1/2 dr r d theta. Yes, yeah, that's precisely what's written. No, you're okay. Plus 1/2 dr times r d theta dt. Now, what happens here is that we can now safely take the limit. Take the limit where dr, d theta, and dt go to 0. And so that implies that this second term here, 1/2 dr r d theta dt, this goes to 0 as well. So we can drop that term. Basically, it has two infinitesimal things, whereas the first term only has one. So the first term is going to be dominant. So what we get is we get that the rate of change of the accumulated area is 1/2 r squared d theta dt. And all of these approximations that we made are exact in the infinitesimal limit. So this is an exact equation that we've written down. And so d theta dt is just omega. So this is 1/2 r squared omega. But we know we can write m times r squared omega as the angular momentum. So this is just m r squared omega over 2m. I just multiplied and divided by m. So this is just L over 2m, which is a constant, because L and m are both constants. And so now let's just check that this implies that you get a constant area for a constant duration. So how do we do that? Well, we have dA dt, just writing down what we had before, equals L over 2m. That implies that dA is equal to L over 2m dt. And so we can integrate, and we get that A has to be equal to L over 2m times delta t. So as long as you fix the value of delta t, let's say you choose 5 seconds, this number is unchanged regardless of where you are in the orbit. So the area is just a fixed number as long as the duration is fixed. So this is just a proof of Kepler's second law. All right, I promise we're on to the last one. Let's talk about Kepler's third law. By the way, maybe I should explain why I'm doing what I'm doing. So I gave you Kepler's laws, and you already knew the formula, so why am I bothering to like show you where they come from? Well, if you want to just use the laws, you don't need to know where they come from. But physics is about you take experimental data, which is what Kepler did, and then you try to come up with a model that explains that experimental data in a simpler term. So what we're doing is we're showing that Newton's universal law of gravitation as a model accurately explains the data that Kepler took, which is a useful thing to do, and that's what physics is about. It's about modeling the data that you get from reality. So let's check Kepler's third law here. Let's check it for circles first, because circles are going to be easier. So remember, Kepler's third law is the statement that the cube of the semi-major axis divided by the square of the period is a constant. So for a circular orbit, the semi-major axis is the radius of the orbit, so we can just use that. So first, in a circular orbit, the velocity is a constant, right? Kepler's second law would tell us that the velocity has to be constant, because the you have to sweep out equal angles in equal time in order for the areas to be the same. And so what we have is that the velocity, which is just equal to the average velocity, is just the total distance covered divided by the time, right? It's a useful equation that we're going to use. Further, Newton's second law gives us the following. And centripetal acceleration gives us negative g capital M little m over r squared. This is equal to m, perhaps with a minus sign thrown in. Let's get rid of those signs. This is just m times the centripetal acceleration, right? All of the acceleration is towards the center of the orbital. Yes, I mean the speed is constant. Yeah, you're right. All of the centripetal acceleration is towards the center, so there's never any tangential acceleration. So this is a perfectly valid statement. We can talk about magnitudes here. But the centripetal acceleration is just mv squared over r. So rearranging, we get that v squared equals gm over capital R, the radius of the orbit. And so we can combine these two equations that I just put in boxes, and we get that 2 pi r over t squared is equal to gm over r, and that gives us that r cubed divided by t squared is equal to g times m, g times, this should be a capital M here, sorry. G times capital M, should be a capital M as well, over 4 pi squared, which is of course a constant. So this is an expression for Kepler's third law. The radius cubed divided by the orbital period squared is a constant. They're proportional to each other. In this case, the radius cubed is the semi-major axis cubed. They're the same thing. Now, what about ellipses? Or ellipses? I feel like ellipses is the correct way to say it. Well, we use Kepler's second law. We're going to have to use Kepler's second law and the area of an ellipse. So if you go back and you look at the area of an ellipse from your geometry class or whatever, the area of an ellipse is pi times AB, where B is the semi-minor axis. It's the shorter axis. And by the way, this shouldn't be surprising. If you use, if you're imagining a circle, the semi-minor and the semi-major axis are the same. So you'd get that the area is pi times the radius, which is pi r squared. Further, Kepler's second law gives us that the area, the total area swept out, or the area swept out over a given time delta t, is L over 2m times delta t, right? That's what I derived up earlier. And so so if we imagine for the entire ellipse to sweep out the entire area of the ellipse, that implies that the area of the ellipse, again from Kepler's second law, is L over 2m times the period that it takes to go around that ellipse. So what we have is that we have pi AB equals L over 2m times t, but we can do some geometry to get out what B is in terms of the eccentricity. It turns out that B squared is equal to A squared times 1 minus E squared, the semi-major axis times 1 minus the eccentricity squared. And so we can do some more algebra, substituting things in. A squared minus 1 over E squared. I'm just squaring the whole thing and then substituting in. This is equal to L squared over 4m squared t squared. And then this is why I boxed that thing earlier. Remember that L squared is related to the semi-major axis, the eccentricity, and the various masses. I'm going to substitute that in for L squared here. And so we get that this is, we get after substituting in, substitute L squared, we get that we get pi squared A cubed L squared over G m squared equals L squared over 4m squared. I know I'm throwing a whole lot of algebra at you, but I promise this is going to be satisfying at the end. And then you get L's cancel, you get the little m's cancel, and you can solve, and you get A cubed over T squared is equal to capital G times capital M over 4 pi squared, which is precisely Kepler's third law. So, and it's the same that we got before. So it turns out you actually don't even need to know the orbit of another body. As long as you know the gravitational parameter of the gravitating body, that's enough to get you the orbit, or the orbital time, because we now know what that constant is. It's G times capital M divided by 4 pi squared. Just a quick remark that I want to make before I continue. So for the first law, we needed the fact that it went as 1 over r squared, that the universal law of gravitation went as 1 over r squared, right? Otherwise, the r's and the denominators would not have canceled out. We needed that fact. For the third law, we needed the first law, right? We needed to know the fact that A, it's an ellipse, and B, that the orbits are closed. So we needed the first law for the third law, and so we also need the fact that you have 1 over r squared behavior for the third law. But we didn't need that fact for Kepler's second law. as long as, so, and this could have been any shape, and you still would have had this triangle-like feature where the area swept out is 1/2 r squared omega. This is just true regardless of the, of whether maybe gravity went as 1 over r cubed or 1 over r to the 4th or whatever. That's still true. So as long as, so all we need here is that you have a central force, i.e. that angular momentum's conserved. So the takeaway here is the second law is a little bit more fundamental. It tells you it's less specific to gravity than the first and third laws are. It's just a little tidbit that I thought might be useful for you guys to know. All right, so that's enough of Kepler's laws. We only have 9 minutes left, and so I'm glad that we do, because I only jotted down a little bit of work for this. This is at the beginning of chapter 7.3. I'm gonna bump over into a different thing so it's bigger. So I hinted that I would talk about gravitational potential energy today, which I'm glad I have the time to do. I know I rushed through that, but you can go back and watch it if you want to see what I did in more detail. So I hinted at the result earlier that the gravitational potential energy should only depend on the radial distance, but I didn't actually tell you what the formula is. Now, in the past, we used the fact that the gravitational potential energy, say as a function of y, was mgy, and maybe we had plus a constant there. But we know that that can't be the case. Sorry. We know that it can't be that way for the actual gravitational potential energy, i.e. for Newton's universal law of gravitation, because this results in a constant force. If you take the derivative of this gravitational potential energy with respect to y, you get a constant force. And remember that the force is related to the potential energy by a derivative. And so we know that Newton's u log, I'll just start saying u log, Newton's u log does not describe a constant force. The force changes with distance. So this can't be right. At best, it's an approximation. However, we do know it is still the case that the u log force is conservative. Conservative. That's how you spell that. Right, like that has to be true. It still has a potential energy. It's still a well, one reason why it has to be conservative is because orbits form, and if it wasn't conservative, then you would expect energy to be lost as you go around an orbit. And unless you consider Einstein's relativity, that's just not true. So hopefully you guys remember how to go from a force to a potential energy, right? You integrate one of the variables, and then you check that taking the derivative of what you got after integrating agrees with the other variable, with the other directions. So let's look at the formula in more detail than we've done before. So with respect to x and y, this is gmm over r squared times r hat, but we actually need to write out what r squared and r hat mean in terms of x and y. So it's a little bit easier to write it out in a different way. So I'm going to multiply it and divide by r. So this is now, all I've done is just said that r vector is r hat. Sorry, r hat is r vector divided by r, right? You just take the vector r and divide it by its own magnitude. So I just rewrote it like this because it's a little bit easier to deal with. So we can rewrite these things in terms of the standard coordinate system, right? If we have some object, say our gravitating object is at the origin like it usually is, this will have some x, y, and z component, and so we can write out what this r is. This vector here is r, and it has length equal to its magnitude. So this is negative g times mm over, now we have x squared plus y squared plus z squared to the 3/2. So r is x squared plus y squared plus z squared with the square root over it all, and then we have to cube that whole thing. And then the vector r is now x in the I hat direction plus y in the j hat direction plus z in the k hat direction. Okay, so far so good. Now, perhaps you can actually already see what's going to happen here. So let's just look at the x component. So the x component of the gravitational force as a function of x, y, and z. This is negative g m m, negative g m m. And then we have times x divided by x squared plus y squared plus z squared to the 3/2. Now, I think that probably some of you are good enough at calculus that you could just integrate this, right? Treating y and z as constants. And I trust that you could. So I'm just going to give you a little bit of a hint here. The partial derivative of, that shouldn't have a vector on it, it's the x component. The partial derivative of the function x squared plus y squared plus z squared to the 1/2, to the negative 1/2, sorry. This is equal to negative 1/2 times 2x times x squared plus y squared plus z squared to the 3/2, which is precisely negative x over x squared plus y squared plus z squared to the 3/2. That's what we had up here. And so what we find then is that if you had wanted to integrate this with respect to x, and then stick a negative sign in front, which is what you have to do, you would find that the potential energy function looks like negative g times capital M over lowercase m. So far, so good, nothing's changed. And then we just have x squared plus y squared plus z squared to the 1/2. Oh, let me move this down because it's kind of taking up 2 lines. And then plus perhaps a constant. And you'll find that this is what it has to be, and you could check that this checks out for all 3 components, x, y, and z components. And so we can rewrite this. We can write this as just a function of r, right? So u as a function of r, I need to make sure I got the sign right. Yeah, I got the sign right. Because remember, when you integrate, you have to stick a negative sign in front too, because f is equal to the negative gradient of u. Remember that means gradient. It means take the derivative in 3 directions. So what we get is that the gravitational potential energy as a function of r is just negative g times capital M times little m divided by r, plus perhaps u naught, but I'm going to drop that. This is the standard formula that we will end up using. It's just more convenient that way. And so what do we find? Well, we find that, oh, I can't scroll up because that was on a previous page. We find that indeed it does only depend on distance. And in fact, you probably could have guessed this formula, right? Just looking at this formula, you say, oh, just integrate with respect to r and stick a negative sign in front, and you'd be correct. That's precisely what happens. But if you wanted to make that formal, you'd have to work in spherical coordinates, which I didn't want to do. So I instead chose to work in Cartesian coordinates, because you guys don't know what the gradient means for spherical coordinates anyway. Right, so this works out. And so now you should precisely have the tools in order to solve the last problem on the homework. The last problem on the homework assignment involves using energy conservation effectively. There's some magic spaceship, and it basically only requires the minimum amount of energy input as fuel. So you're going to have to use this formula to find the potential energy and kinetic energies at various places and speeds in the solar system. And noting the fact that that energy is conserved when there's no external, when it's just you and another thing, then gravitating against each other, then you can use kinetic energy and plus potential energy as a total energy, which is conserved. Right, sorry I went very, very fast. I had to get to this so you guys could do the last homework problem. I'm going to stop the recording here.